welcome to our session, Physical Sciences. My name is Gr11. Today we are looking at Coulombs Law, but with a particular theme of forces between charges. This is what is of interest to us. We know that already, that if we've got any 2-point charges in space, they actually exert a force on each other. And every force is actually an applied force. I think in the context of electrostatics, we talk about force by charge A on charge B and vice versa. That is force by charge B on charge A. So we want to investigate exactly what happens in terms of the forces. And we also need to keep in mind that forces are actually vectors. So the emphasis is on both magnitude and direction. So we'll carry out some demonstrations to actually discover some of the very important aspects of the Coulombs Law. This is what is our core focus for today. Right, just to get us started as an icebreaker, we've got a concept map. So today we are looking at field forces which are non-contact with respect to the Coulombs Law. What we already know is that between any 2-point charges, there is an electrostatic force that exists between them. That force can either be attraction or repulsion, but our main focus is on the Coulombs Law, right? Now, the thinking part is the key thing for today. Have you ever thought about the factors? Factors are usually quantities, are usually physical quantities, right? These are usually physical quantities, right? Have you thought about the factors, quantities, right? Okay. Have you ever thought about factors that affect the magnitude and direction? The moment we say magnitude and direction, what comes to mind, because we are talking about forces between charges, we're thinking about vectors. So that's the key thing here, of the force exerted on a charged object. But remember, every force is an applied force. We can talk about force exerted by, as an example, force exerted by, okay, just to bring this into context, by charge 1 on charge 2. So the main thing about forces as vectors is that a force is always exerted by something on an object. So in the context of charges, we can take, for example, charge 1 and charge 2. So our main idea here is to look at which factors exactly affect the magnitude and direction of the force. Now, what kind of a force are we talking about here? We're talking about the electrostatic force, right? What's so important about the electrostatic force is that an electrostatic force is a non-contact force, right? It is a non-contact force, right? Now, if we are to break it down, if we talk about a non-contact force, as an example, a magnetic force is a non-contact force. The gravitational force can be, a non-contact force, as well as the electrostatic force. Okay. Now, what's so common about these forces that we've mentioned as examples of non-contact force is that exactly these forces are actually field forces. They act on one object by another over a distance, and the concerned objects need not to be in contact with each other. So hence we talk about the field forces and non-contact forces in the context of electrostatics. Right, okay. Now, the key words, terminology is very important. If we are to investigate, okay, if we talk about a scientific investigation, right? If we talk about an investigation, sometimes we can talk about an experiment, right? Where we want to verify an existing scientific fact. In an investigation, we want to also, discover something, based on what we already know. So we talk of variables. So a variable is essentially something that changes. Now, if we talk about an independent variable, we're talking about that physical quantity that is manipulated, okay? The physical quantity, okay? Physical quantity, right, that is manipulated, okay? So what do we mean when we say it's manipulated, okay? We are saying that as experiment experimenters or investigators, we can actually change that variable to see exactly how it affects the other one. So we'd call this the independent variable. Take note of that, okay? And it's always a physical quantity, right? And then we also talk about the dependent variable, right? So the dependent variable, in other words, you may refer to it as the response variable, okay? So this is our response variable. In other words, changing the independent variable, we want to see how it affects the dependent variable. Hence, this is our response variable, as the name suggests, right? And then we've got the controlled. Controlled is the one that always remains constant, right? So this one remains constant, right? If I can make an example, for argument's sake, we want to establish who is faster between athlete A and athlete B. The two athletes have to run the same distance, okay? Then we'll say, okay, how much time does each one of them take to complete the same distance? So the same distance is essentially, the controlled variable. And then we want to see how fast. Obviously, it will talk to the amount of time taken to complete that distance. So the time taken becomes the response variable or the dependent variable. Just to put that into context, as we'll establish as we look further, okay? And then we talk of the other word that says directly proportional. This is a mathematical relationship, okay? If two quantities are directly proportional, what does it mean? Okay, if one increases, all right? And then we're talking about the independent variable. If one quantity increases, right? So if one quantity increases, for argument's sake, okay? And this quantity is the independent, right? The one that is manipulated, okay? The independent, okay? If one quantity increases, which is the independent, the other one also increases. The other one, so the other one here in this case is the dependent or the response variable. Dependent, okay? Okay. The dependent also increases, right? As an example, but in the same proportion, to qualify that, in the same proportion. So that's what is very important as far as directly proportional is concerned. So if you increase the independent variable, the dependent variable in response will also increase, but in the same proportion. Equally so, if we decrease the independent variable in terms of magnitude, the dependent variable will also decrease in the same proportion. So I want us to emphasize on the proportion, because that's what it's all about, right? And then the other term is inversely proportional, okay? Now, if we talk of two quantities or variables becoming inversely proportional to each other, what that simply means is that when one increases, the opposite happens to the other. But the issue of proportion also comes through as well. If one increases, the other one decreases, but in the same proportion. If the one decreases, the other one increases. So the opposite is true in as far as inversely proportional. Take note, we do not talk about mathematically indirect proportion. It's direct or inverse. So let's just get that out of the way. All right, okay, moving along. The other one is reciprocal. So there's a lot of mathematical language. A reciprocal is not an inverse. So let's say, for argument's sake, we've got A as a quantity. So the reciprocal of A is actually 1 over A, right? So this is what it means. So this is not an inverse. It's actually, we call it a reciprocal. So we'll talk about, for argument's sake, the reciprocal of the square of the distance, which is 1 over r squared. So this is the reciprocal of the square of the distance as an example, right? Okay, now those are the key terms in as far as the mathematical relationship is concerned. But remember, our main focus for today is to try and discover some of the factors that affect the magnitude of the electrostatic force that exists between any 2-point charges in space, which takes us exactly to the Coulombs law. So the Coulombs law actually talks about any 2-point charges. Now, when we talk about factors, we are essentially referring to the physical quantities. So those physical quantities can either be one, product of charges, right? Product of charges. Now, and when we talk about product of charges, say for argument's sake, we've got Q1 and Q2. Product is the multiplication Q1 multiplied by Q2. So this is what we refer to as the product of charges. Okay, in other words, it can be anything. It can be QA, QB, as long as there are 2-point charges, because the Coulombs law tells us something about any 2-point charges in space. Or we can talk about the square of the distance, okay? The square of the distance, okay? Of the distance between any 2-point charges, okay? So the distance is between the charges, okay? Now, we're also tempted to address something that's very, very critical, the difference between the Coulombs law and the law of universal gravitation. There are some similarities as well as differences. Now, just to get that out of the way, let's understand, in nature, point charges are actually very minute particles, such that we can even ignore the internal diameter of each one of them. So as that is the case, we are saying that the square of the distance is between the charges. While if we go to the universal gravitation, we talk about the square of the distance between the centers. So that's the main differences. So if for argument's sake we talk of universal gravitation, is the force of gravity, okay, which is the always attraction, which is G m1 m2 over d squared, right? So here it's about the masses, okay? So this is about the product of the masses, okay? So this is the product of masses, right? Okay. It's never about the charges, while on the other end, if we talk about the electrostatic force, it's K, Q1, Q2 over R squared. So what about this? This is the product of the charges, okay? So that's the product of charges, okay? Right. So the main difference is that when we talk about the universal gravitation, we're actually talking about the distance between the centers, because the force of attraction is measured from the center of each of those two objects. But here we talk about charges. So this is about the charges, which is the Coulombs law, while the universal gravitation is about, the masses of objects. And also there's a difference between the gravitational constant, which is G, okay? This is the constant, okay? And take note, this is different from the other G, which is the acceleration due to gravity, just to get that out of the way. And then we also have K, which is 9 times 10 exponent 9, okay? Newton meter squared, which is the SI unit of the Coulombs constant. So today, our focus is on this instead of the universal law of gravitation. Clearly, the difference between the two must be very clear from the onset, right? Having said that, let's take a short breather, and then when we come back, we'll look at typical examples using a simulation, something that's very exciting, and also it will help us to try and conceptualize the whole idea around the Coulombs law. Let's take a short breather for now. Welcome back to our second segment of our session. Today we're looking at forces between charges. Now the main idea in this session is to actually look at the factors that actually affect the magnitude of the electrostatic force between any 2-point charges. We've also spoken to the language in terms of the variables, which is your dependent, independent, as well as the controlled variable. So what we're going to do, we're just going to explore the Coulombs law and try and discover some of the very important aspects of the Coulombs law in terms of understanding. Now, as part of our investigation, we want to predict what happens to the magnitude of the force. Okay, I'm going to underline force when the size of the charge changes. Okay, so what exactly are we saying here? We need to identify our variables. So the effect of changing the magnitude of the charge on the force, it immediately says to us that the electrostatic force is actually the dependent variable. Okay, we've already spoken about the dependent variable and what exactly it's all about. So we want to see how the magnitude of the electrostatic force is affected by changing the charge. So charge of one of the two charges is going to be changed. So this charge which we change or manipulate is actually our independent variable, right? So that's our independent variable. So it's very important for us to actually identify our variables from the onset, right? So what we're going to keep the same in this case is the distance between the two charges, Q1 and Q2, right? Now, as part of our prediction, here is a scenario here. If we go back to that slide, we'd see immediately that if the distance between their centers, between the two charges, remember these are charges, okay? If the distance between them is actually 3 centimeters, we can actually measure that. So the 3 centimeters is the distance between Q1 and Q2. The force exerted by Q1 on Q2 is 9,986, which is approximately 10 newtons. It's the same magnitude, but you must realize that these two forces are actually in opposite directions, right? Now, if we go to our table, it says here when the charge of Q1 is -1 and that of Q2 is +1, the distance is 3, that's the force that we have recorded. So our intention is to populate and collect the data so that we can kind of analyze the trend or pattern so that we can come to a conclusion as to how does changing the magnitude of the charge actually affect the magnitude of the electrostatic force. Now, you'd realize that the distance between the two charges is the same. So in other words, distance R is the controlled variable, right? So R is the control variable, okay? Okay. Now we're keeping R constant as well as the magnitude of charge of Q2, okay? So Q2 and R are actually control variables. The only thing that we're changing is the magnitude of Q1. So now we are going to double the size of the charge of Q1 and keep the distance the same as well as the magnitude of charge of Q2 so that we can populate our or collect our data so that we can make those important predictions. So now let's go straight to our simulation, right? So this is our simulation. You can see the Q1 is -1, Q2 is +1 microcoulombs. And the distance between them, we can actually measure it like that. It's exactly 3 centimeters, right? So that's the distance over there. Okay, we're not going to change the distance. Why? Because the distance is our controlled variable. So what are we going to do now? We're going to double the charge of Q1. So if we double the charge of Q1, Q1 becomes -2 microcoulombs. Clearly you can see that. Now you can immediately see that the force exerted by Q1 on Q2 almost doubles, that is 19,9, which is approximately 20. The same happens on the force on Q2 by Q1. So if we go back to our table, okay, we know that this is 19,99, okay? That's 19,99 newtons, okay? Now, in the third trial, what are we going to do? We'll make charge Q1 3 times as big as its original charge. So we go back to the simulation, okay? Now, if we make it 3 times, it means it's going to be -3. So if we make it -3, you can see immediately it's 29,959, okay? So the charge keeps on increasing while we're still keeping the distance between Q1 and Q2 the same. So this is 29.9, okay? We'll go back to our table. This is 29,9. Clearly we are getting the trend in this case, the pattern. Now, the last trial says that Q1 must be 4 times as bigger as its original charge. So if it was -1 at the start, now it's -4. Let's see the final value so that we can make a comparison and look at the pattern in terms of how does changing the charge of Q1, only keeping the distance the same and the charge of Q2 the same, how does it affect the magnitude of the electrostatic force? So if we go back to our simulation, we'll make Q1 -4. Already we've changed it. It says 39,9, right? So that's the magnitude. And what you also need to realize is that the force exerted on Q1 by Q2 is equal in magnitude to the force exerted by Q2 on Q2 by Q1, but their direction is opposite, right? So in this case, the magnitude of the force that we need to complete our table is 39,9, right? So if it's 39,9, that's the magnitude of the force. Now, immediately we can pick up as the magnitude of Q1 increases while the distance between the two charges and the charge of Q1 remains constant, the magnitude of the electrostatic force also increases in the same proportion. This is what we emphasized, okay? Now, having said that, we see that, okay, the force, this is basically what we have seen from the simulation. These are the values that we have confirmed, all right? So this is what is going to happen in terms of the magnitude of the force. Now, this one says predict what happens to the magnitude of the force when the size of the charge changes. So this is what, at the end of the day, we want to arrive at. Okay, but now, if you look at this slide, Q1 is actually -2 microcoulombs, right? While Q2 is equals to +2 microcoulombs, right? So these are the initial values. The distance is 3 centimeters apart, okay? Now, if we move to the next, we would want to see what exactly happens. The distance stays the same, but now you have to realize that we are changing both charges. Now, the initial value of, if we can go back to our simulation, we started at -1, okay? -1 for Q1, okay? -1, there we go, right, for charge 1, and then this one is +1. So the force is 9,986, right? So we are going to double both charges, okay? If we double both charges, if we go to our simulation, we have to double both charges in this case. Now, Q1 becomes -2, while Q2 becomes +2. Then we want to see how that will affect the magnitude of the force, so between them. So we have doubled Q1, okay? We are also doubling Q2. Already, the force has also, increased by the same proportion, which is now is going to be 39,9. So if we go back to our table, we'll write here 39,9 newtons, right? Now, we make them 3 times as bigger, both of them, and see how that affects the magnitude of the force between them. So this becomes -3, while that becomes +3 microcoulombs. Already, this is even bigger. It's almost 90, which is 89,9 newtons, if you can round it off. So it's 89,9. So this is 89,9 newtons. I think you pick up the pattern. And if we make them 4 times as bigger, we double both charges, okay? So if we double both charges, it means Q1 becomes -4, while Q2 becomes +4 microcoulombs. This is 159,9, which is more or less 160. But I think we're getting the pattern here. So it's 159,78, okay? Right, 159,78. Now, wait a minute. There is a pattern here. As we double the product of the charges, what's happening to the magnitude of the electrostatic force between them? So this is exactly what's happening in terms of the factors. So if we move a step further, this is the main thing. So the factors that affect the magnitude and direction of the force exerted on a point charge by another. So this force is directly proportional. So the product of the charges, as the product of the charges increases, the electrostatic force between those two charges increases. So mathematically, we can say the electrostatic force is directly proportional to the product of the charges, right? So this is what we wanted to arrive at the end. So you also realize that if the product of the charges increases, so does the magnitude of the electrostatic force in the same proportion. So the smaller the product of the charges, the smaller the electrostatic force between those 2 point charges, right? Which is a very important thing that we wanted to actually discover. So that's the main idea. The product of the charges affects the magnitude of the electrostatic force. So in other words, the electrostatic force between any 2 point charges is actually directly proportional to the product of the charges. So increasing the product of the charges increases the force by the same proportion, which is basically what it means when it comes to 2 quantities becoming directly proportional to each other. Having said that, let's take a short breather. We'll explore more aspects of the factors that affect, the magnitude of electrostatic force in as far as the Coulombs law is concerned. Let's take a short break for now. Welcome back to our third and final segment of, investigating the factors that affect the magnitude of the electrostatic force between any 2 point charges. This is with respect to the Coulombs law, as you'd know it. Now we have managed to look at how, the product of the charges affects the electrostatic force. Now let's change our gears and look at the distance between any 2 point charges. How exactly does it affect the magnitude of the electrostatic force as suggested by the Coulombs law? Right. Now, we have a scenario here which says predict what happens. So it's all about predictions. Predict what happens to the magnitude of the force. So the electrostatic force in this case still remains our dependent variable. We're going to change the distance between the charges. Now the distance is our new independent variable. In other words, so the magnitude of the charge will remain constant, right? The only thing that we're changing is actually the distance, right? Now, we've got 2 point charges, Q1 and Q2. Each of magnitude, Q1 is -1, okay? Q1, if we can collect our data, Q1 in this case is equals to positive, negative rather, okay, that's negative. Let's correct that, right? So Q1 in this case is given as -1 microcoulomb, okay? While Q2 in this case is a positive 1 microcoulomb. So these are essentially opposite charges, right? So in other words, there is an electrostatic force that exists between them, and the distance between them it is measured from those 2 imaginary lines is actually 3 centimeters, okay? So we'll change the distance while keeping these 2 the same, and we want to see how it affects the magnitude of the electrostatic force, right? Now, in the table of results, you can see that the distance is what is changing while both charges remain constant. So the product Q1, Q2 is controlled, okay? Why are we saying that? It's because we're not changing the magnitude of the product of the charges, or either we're not changing the magnitude of each charge, which actually affects the product anyway. But now what is changing here is our distance between the 2 charges. So this distance R is actually our independent variable, right? So by changing R, we want to see how it affects the magnitude of the electrostatic force that exists between Q1 and Q2. So if we go back to our previous slide, you'd realize that the force is given when the charge is -1 and +1 and the distance is 3 centimeters, the force is actually 9,9, which is approximately 10. So this is what it says here, but if it's 2 centimeters, it's going to be that. Let's actually go to our simulation and check if what happens if it's actually 2 centimeters. So 2 centimeters, very careful about that. I'll put Q1 there on the 0 to make the measurement easier. Okay, there is the force. Okay, there is the force. I must change this one to -1. Okay, Q1 must be -1 microcoulombs, while this one becomes +1. And let's see how it affects the force. So the force is actually 22,46, right? So this is what it suggests. If we go back to our table, this is the actual force that the distance is 2 centimeters, okay, while the force is 25,9. And then when we increase the distance between them to 3 centimeters, let's see exactly what happens. So the force is affected by distance, okay? So the distance must be 3 centimeters now. What exactly happens? There is the force. Now the force is 9,986. We have made the distance 3 centimeters between Q1 and Q2, right? So that is 9,9. So if we go back to our table, this gives us 9,9, okay, newtons, right? So there's a decrease there. What if we make the distance 4 centimeters? Let's see what happens. Okay, if we go back to the simulation, now the distance must be 4 centimeters. I think we can almost predict. Now it's 5,617, okay? We go back, 5,617, okay, 62, okay, newtons. I think you can immediately pick up the trend. The greater the distance between the charges, the lesser the force becomes, okay? Are we on to something? Now let's make the distance between them 8 centimeters for argument's sake, okay? If we make the distance between them 8 centimeters, let's move these around so that we create space. So that's 8 centimeters. We take this one there. Now it's 1,4 newtons, okay? Even smaller. So we go back to our table, 1,4 newtons. Now, what's the pattern that we are getting here? As the distance between the charges gets bigger and bigger, how does it affect the force? The force gets lesser and lesser. But let's pay attention to the proportion in which the force is decreasing while the distance increases, right? So if we move forward, the question says, what happens to the force when the distance between the charges increases? We know that the electrostatic force decreases, okay? So the electrostatic force decreases. Okay, there's a decrease in the electrostatic force. But if we decrease the distance, so it means if we go back here, we would say moving upwards from 8 centimeters to 2 centimeters, what is happening to distance? Distance is actually getting shorter and shorter. What's happening to the magnitude of the electrostatic force? It's increasing. So we can safely say that if the distance between the charges, the electrostatic force will increase, right? So the electrostatic force between those two charges increases, right? Are we onto something here? Because we are worried about the mathematical relationship in terms of the factors that affect, the magnitude of the electrostatic force. So this is the gist of exactly what we want to discover or arrive at. Right, now here's a graph that shows exactly what happens, okay? So it says here what happens to the force when the distance between the charges it changes, okay? Now we are saying here, the mathematical relationship, we are saying that the electrostatic force is inversely proportional to the square of the distance. So if the square of the distance increases, what happens to the electrostatic force? Let's check that. So this is a smaller value of r squared. It means there is a shorter distance between the 2 point charges. There is the magnitude of the force. What if we make the square of the distance between them greater? What exactly happens? You'd realize that if let's say this is F1, okay, and then that is F2. What are we saying exactly? If the square of the distance increases, the magnitude of the electrostatic force will actually decrease, which is exactly what this is all about. Okay, that's the main point, that the square of the distance and the electrostatic force are actually inversely proportional to each other. Right. Now, here's something that is also very important. Now, if we are saying that the electrostatic force is inversely proportional to the square of the distance, okay, we are also saying that at the same time, the magnitude of the electrostatic force is directly proportional to the reciprocal of the square of the distance. So 1 over r squared is actually directly proportional to F, or F in principle is directly proportional to the reciprocal of the square of the distance between the charges. Hence, we get that linear graph. So when 1 over r squared increases, then the force will also increase. So this is the main idea in as far as, you know, the distance as well as the product of charges, and as far as the Coulombs law is concerned. Right. Now, this is what it's all about. This is what it all boils down to, because we were so concerned about the Coulombs law and what exactly it means when we say two quantities are directly proportional while others are inversely proportional. It says here the magnitude of the electrostatic force exerted by one point charge Q1 on another is directly proportional, okay, to the product of the charges. So we are saying F, which is the electrostatic force, is directly proportional to Q1, Q2. So this is what we mean when we talk about the product. So the product is the multiplication of the magnitude of the two charges involved, while at the same time we're saying it is inversely proportional to the square of the distance. Take note, square of distance is different from square root. Okay, so that's one of the things that obviously come up. You know, if we talk about the square of the distance, in this case it's r squared, which is totally different from square root. So we need to have a clear distinction in as far as those two are concerned. Right. So here, what are we saying? We are saying F, which is the electrostatic force, is inversely proportional to the square of the distance, which gives us at the end F is proportional to Q1, Q2, right, over r squared. So there are two aspects to the definition of Coulombs law, that of directly proportional as well as inverse proportionality, right? Okay, now let's look at the data sheet. Okay, the data sheet is, this is what is going to be given to you as in the formula sheet. Okay, so from mathematically looking at that, you can see the product of the charges, you can see the square of the distance. So this is the product of charges, right? So that's the product of the two charges, point charges concerned, and then the square of distance, okay, between the two charges. So that's the square of distance. So which mathematically gives us that Coulombs law, whereby K is that constant, okay? The units Newton meter squared per Coulomb squared. So you need to also be familiar with that and distinguish it from the G, which is the universal gravitational constant, right? Now, in terms of applying the Coulombs law, multiple choice questions if we've got a special focus on the conceptual understanding of any physics concept, right? So you need to be able to apply the Coulombs law, you know, appropriately based on your understanding. Because after investigating the factors, we've realized that there are two main things that actually affect the magnitude of the electrostatic force. One is the product of the charges, the 2-point charges, okay? And also the square of the distance between the two charges. Now, if we talk of direct proportionality, it has to do with the product, how it affects the electrostatic force. And in both cases, the electrostatic force is always the dependent variable. And then again, here it says as an example, the magnitude of the electrostatic force exerted by 1-point charge, Q1, on another is Q2. So our force is equals to 16 newtons is given, okay, right? Now, what happens to the force when the charge on Q1 is doubled? Now, if we double Q1, it means, in other words, we are saying that the 16 newtons is equals to K, Q1, Q2, whatever Q1 is and Q2 is r squared. The assumption here is that we keep the distance the same. So if we double Q2, we double Q1, we'll have K2 Q1, right? Q2 over R squared, right? Now, if we're saying this is equal to 16, mathematically left-hand side is equal to right-hand side. So this term on the right-hand side is equal 16. So I want to express the new force in terms of 16, right? This is going to be 2K Q1 Q2 over R squared. So this is like 2 multiplied by 16. So if we double one of the charges, the actual force will be doubled. So the new force will be equals to 32 newtons. So this is what it's all about. That's what it means when you say the product of the charges is that it affects the electrostatic force. So the electrostatic force is directly proportional to the product of the charges. So if we double the product, the electrostatic force will also be equivalently doubled, right? And then the magnitude of the electrostatic force, still the same, 16. What happens to the force when charge Q, both of them are doubled? So in this case, we have got K, 2Q1, we've doubled Q1. 2Q2, we've doubled both charges, we've kept the distance the same. So this is like 4K Q1, Q2 over R squared. Now we know that this is our 16. So this is the new force will actually be 16 multiplied by 4, which is 64 newtons. So as the electrostatic force, as the product increases, so does the magnitude of the electrostatic force. Now, having said that, I think it's proper for us to appreciate that if we understand the concept of what exactly it means when we say that two quantities are directly proportional, how exactly does it affect the other one? So that's the long and short of it. And then last but not least, let's look at a scenario which involves the distance. It says, what happens to the force? Okay, how does it affect the force when the distance is doubled? Okay, so what we know is that 16 is equals to K Q1 Q2 over R squared. Okay, now we're going to double the distance. So this is our 16. So if we double the distance, it's going to be K Q1 Q2 over 2R. Now we are squaring 2R. Take note of that. Okay, so if we square 2R, this reduces to K Q1 Q2 over 4R squared. Okay, so this is like 1 over 4K Q1 Q2 over R squared. So that's our 16. So the new force will actually be a quarter of the original one. Actually, the force has actually decreased because we've doubled the distance. That's the inverse proportionality. So the new force will be a quarter of 16, which is actually 4 newtons, right? So this is how exactly we apply these. But the main thing, again, that we also need to take into account is the fact that whatever force charge 1 exerts on charge 2, it's equal in magnitude to that exerted by charge 2 on charge 1, but opposite in direction. Now, we're onto something. It obviously takes us to the Newton's third law, right? The forces are equal in magnitude, but opposite in direction. So that's as far as, the factors that affect, the magnitude of the electrostatic force in terms of distance and the product of the charges. Having said that, hopefully this has made a lot of sense in terms of trying to unpack the Coulombs law. And because of time constraints, we've reached the end of our session today. For myself, Gr11 PS is cheers and bye-bye for now.